Hello everyone, I am Sweta from GMRP Dutchwell. In this video lesson, I am going to discuss about the block diagram of continuous wave radar. Draw and explain the block diagram of continuous wave radar. List the limitations of continuous wave radar. Draw and explain the block diagram of moving target indicator radar and also principle of instrument landing system. So first of all, we'll discuss about the block diagram of continuous wave radar. So this is the block diagram of continuous wave radar. The continuous wave radar uses the Doppler effect to detect the frequency change caused by a moving target and displays this as a relative velocity. Okay. So in continuous wave radar, which uses the Doppler effect to detect the frequency change caused by a moving target and displays this as a relative velocity. Doppler effect means the frequency shift in the received echo signal in the radar due to moving target is known as a Doppler effect. Okay. So the frequency shift in the received echo signal in the radar due to the moving target is called as a Doppler effect. So the Doppler effect or the Doppler frequency shift is given by Fd is equals to 2Vr by lambda. Okay. So that is about the Doppler frequency and Doppler shift frequency. Here the continuous wave transmitter. So this is the block diagram of continuous wave radar. In that this block diagram consists of a continuous wave transmitter, transmitter mixer, oscillator, receiver mixer, IF amplifier, detector, Doppler amplifier, frequency counter and indicator and aircraft and moving target. So this is all about, this is the block diagram of continuous wave radar. So in this, the continuous wave transmitter will produce us a continuous wave with a frequency of Ft. Okay. So which will produce the frequency of Ft. This signal is radiated towards the target. This signal is radiated towards the target by using a transmitting antenna. By using this transmitting antenna, the signal Ft is radiated, okay, towards the target. Okay. Next, the transmitted signal Ft. Here the transmitted signal Ft and the oscillator frequency Fi. Here the oscillator frequency is Fi. Sorry, ikkada Ft padindi. This is Fi are mixed in the transmitter mixer to produce the some frequency that is Ft plus Fi. Okay. So here the receiving echo signal, the receiver mixer function is the receiving echo signal that is Ft plus Fd plus or minus Fd and the transmitter mixer output that is Ft plus Fi are mixed up in the receiver mixer here to produce the output of Ft plus or minus Fd. So here the receiver mixer function is, it is used to mix the transmitter mixer output and receiver mixer input, that is Ft plus Fi and Ft plus or minus Fd. So overall output is Fi plus or minus Fd, that is equals to Fi plus Ft minus of Ft plus or minus Fd. So overall is equals to receiver mixer output is Fi plus or minus Fd. So here the receiver mixer output is amplified by using this IF amplifier. The IF amplifier output is demodulated in the detector to produce the Doppler frequency Fd. Here it will produce the Doppler frequency Fd. Okay. So it eliminates the echoes from the stationary targets and to amplify the Doppler echo signal, that is Fd. So the amplified Doppler frequency Fd is displayed as the velocity of the target in kmph or miles per hour in the frequency counter and indicator. Okay. So in this the Doppler frequency will be indicated in terms of the kmph or miles per hour. So this is all about continuous wave radar. Okay. So once again I will repeat once, see here. So here the continuous wave transmitter will produce the continuous wave frequency of Ft. So this signal is radiated towards the target by using this transmitting antenna. Okay. So the transmitted signal, that is Ft, and IF oscillator frequency Fi are mixed by using this transmitter mixer, and it will produce the output as Ft plus Fi. Okay. So next the receiving echo signal. The receiving echo signal, that is Ft plus or minus Fd, and the transmitter mixer output Ft plus Fi are mixed up in the receiver mixer to produce the output of Fi plus or minus Fd. Okay. So the receiver mixer output is amplified. Next, the receiver mixer output is amplified by using this IF amplifier. Okay. The IF amplifier output is demodulated in the detector to produce the Doppler frequency, that is Fd. Okay. So here in a Doppler amplifier, it eliminates the echoes from the stationary targets and to amplify the Doppler echo signal Fd. Okay. So after that, the amplified Doppler frequency Fd is displayed as the velocity of the target in kilometers per hour or miles per hour in frequency counter and indicator block. Okay. So this is all about continuous wave radar. Okay. So once see here, the continuous wave transmitter will produce the continuous wave frequency of Ft. So here this signal is radiated towards the target by using this transmitting antenna. So here the transmitted signal Ft and the IF oscillator frequency Fi both are mixed by using this transmitter mixer Fi plus Fi. So the echo, once see here, the received echo signal and transmitter mixer output, okay, both are mixed by using this receiving antenna. So overall output is Fi plus Fd. Okay, Fi plus or minus Fd. Okay. So after that, the mixer output is amplified by using a IF amplifier. So IF amplifier output is demodulated by using the detector to produce the Fd, that is Doppler frequency, that is amplified by using Doppler amplifier. Here the echoes, which eliminates the echoes from the stationary targets, and the output is indicated by using this frequency counter and indicator. Here the velocity of the target will be displayed. Okay. So this is all about continuous wave radar. So in that, and also the applications of continuous wave radar. So it is used to measure the speed of automobiles, guided missiles, crickets and tennis balls, etc. Next, it is also used to measure the speed of aircrafts and police radars and to determine whether the target is approaching or moving away. So these are all applications. These are all the applications of CW radar. Next, coming to the limitations. So limitations such as it doesn't give information about the range. If there is a large number of targets, it does not give an accurate results. In continuous wave, it does not give any information about the range. Okay, if there is any number of targets or more, it does not give an accurate result. Next, coming to the advantages. So here the accurate measurement of relative velocity of the target will be assured, and a simple circuit, low power consumption, size of the equipment is smaller than of the pulsed radar. It is used at a low transmitting power. Okay, so these are the advantages of the CW radar. Next, coming to the block diagram of moving target indicator radar. Okay, so MTI means moving target indicator radar. So here the system can determine the moving target velocity. Okay, so the drawback of that is here it is MTI radar is used to determine the moving target velocity and to distinguish moving targets from stationary targets. This improved system is called as a MTI radar. Okay, so here the basic principle of MTI radar is to compare a set of received echoes with the previous received echoes and cancelling out the stationary or permanent echoes whose phase remains unchanged, but moving targets will give a change of phase. That's why these are not cancelled. So the main principle of this MTI radar is it is used to determine the or it can determine the moving target velocity. Okay, and also distinguish the moving targets from the stationary targets. So thus the clusters due to stationary or permanent targets and naturals are removed from the display and easy to detect the moving target. So it can eliminate the clusters of the permanent targets or stationary targets. It can that's why it can detect the moving targets range. So here the MTI radar means moving target indicator radar. It is mainly used to detect the moving targets only. That's why we call it as a moving target indicator. Okay, here this MTI radar uses Doppler effect for its operation. So it eliminates the clusters due to stationary objects and identifies the moving targets. So this is the block diagram of the MTI radar. Okay, so here okay, this is the block diagram of the MTI radar. Here the MTI radar means moving target indicator radar. It is mainly used for detecting the moving targets. That's why we call it as a moving target indicators. Okay, so here the MTI radar uses the Doppler effect for its operation, and also it eliminates the clusters due to the stationary objects and identifies the moving targets. Okay, so the input to the mixer one. So one see the block diagram here. The input to the mixer one is from two oscillators. So the input to the mixer one is from two oscillators, that is Stallo and Coho. That is the names Stallo means stable local oscillator. Coho means coherent oscillator. The output of the mixer 1 is F naught plus Fc. Okay. So here the mixer 1 output is amplified for providing a high power pulse by using multi-cavity Klystron amplifier. So this transmitter pulse is then radiated into space. Okay, so the transmitter pulse is radiated into space by using this duplexer. Okay, so once again I will repeat here. See here. Here the input of the mixer 1 is from two oscillators. The two oscillators are Stallo and Coho. Stallo means stable local oscillator. Coho means coherent oscillator. Okay. So here the output of the mixer 1 is F naught plus Fc. Okay. So here the output of mixer 1 is amplified by using this Klystron amplifier. So this Klystron amplifier will provide a high power pulse. Okay. So that high power pulse is radiated into space by using this duplexer. Okay. Next, the echo pulse. The echo pulse from the target is, okay. So the echo pulse from the target is received by the MTI radar antenna. If the echo is due to the moving target, the echo pulse undergoes a Doppler shift. Okay. So the echo pulse means received pulse. Okay. That is received by using this receiving antenna. Okay. So the received echo signal is F naught plus Fc plus or minus Fd. Okay. The received echo signal is slow bar. Okay, here the received echo signal, that is F naught plus Fc plus or minus Fd, and Stallo output F naught. Okay, and the Stallo output F naught are then passed through this mixer to produce a difference frequency, that is Fc plus or minus Fd. Okay. So the mixer 2 output is Fc plus or minus Fd. The inputs of the mixer 2 is F naught and F naught plus Fc plus or minus Fd. Okay. So the two mixer 1 and mixer 2 are identical in all aspects, except that mixer 2 produces a difference frequency, whereas the mixer 1 produces the sum frequency. So here the mixer 1 produces the sum frequency, here the mixer 2 produces the difference frequency. So that's why the output of mixer 2 is Fc plus or minus Fd. F naught will be cancelled here. Okay. So here next, the difference frequency, that is Fc plus or minus Fd, is amplified by using an IF amplifier and is given to the output of this amplifier is given to the phase detector. Okay. So here the phase detector compares the IF signal. Okay. Here the phase detector will compare the IF signal with the reference signal from the Coho. The frequency produced by the Coho is same as that of the IF frequency, and hence it is called as a coherent frequency. The detector will provide an output depending upon the phase difference between these two signals. Okay, so the output of phase detector is Fd. The phase detector gives the output for both fixed and moving targets. The Doppler shift causes the variations in the phase difference. Okay. So here the detector output, here the output of the detector will goes to the delay line Okay, the output of the detector goes to delay line and amplifier 1. Okay, the delayed output is, one see here, the delayed output is amplified by the amplifier 2, and at the same time the undelayed output of the detector is amplified by the amplifier 1. One see here, phase detector output is given to both amplifier 1 and delay 1. Okay, so here the undelayed output is amplified by using this amplifier 1 circuit, and the delayed output is amplified by using amplifier 2. Okay, next the amplifier 1 and amplifier 2 outputs are given to the subtracting circuit. Is in this, the echoes of the constant phase due to the stationary targets are out cancelled out, but the echoes of the changing phase due to the moving targets are not cancelled. So the subtractor circuit output is moving target echoes goes to the display unit. Okay, so here the limitations of MTI radar is blind speed that is avoided by using varying PRF, that is pulse repetition frequency. So this is all about MTI radar. Okay. Okay, one see here, the input to mixer 1 from the two oscillators, namely STALO, that means stable local oscillator, and coherent oscillator. So the output of mixer 1 is F0 plus Fc. One see here, the output of mixer 1 is F0 plus Fc, that is amplified by using this Klipschon amplifier. So the mixer 1 output is amplified for providing a high power pulse by using a multi-cavity Klipschon amplifier. This transmitter pulse is then radiated into space by using this duplexer circuit. Okay, the output of the amplifier is radiated into space by using this duplexer circuit. Yes, so the echo signal from the target is received by MTI radar antenna. Okay, so see here, here see here, in mixer 2, the echo pulse from the target is received by using this receiving antenna. If the echo is due to the moving target, the echo pulse undergoes to the Doppler shift. Whenever the echo pulse is a moving target device, then that will be undergoes into a Doppler shift. Okay, so here the received echo signal, that is F0 plus Fc plus or minus Fd, and the STALO, that means stable local oscillator output F0 are then passed through this mixer 2 to produce the difference frequency as Fc plus or minus Fd. So here the mixer 1 acts as a summer circuit and mixer 2 will act as a differentiator or subtractor circuit here. Okay, so after that the difference frequency is amplified by using this amplifier. Okay, so the output of this amplifier is next given to the phase detector. The phase detector, one of the input is IF amplifier output and one more is coherent output. Okay, so here the detector will compare the IF signal with the reference signal from the coherent. So the frequency produced by coho is same as that of the IF frequency, and hence it is called as a coherent frequency. The detector provides an output depending upon the phase difference between these two signals. The phase detector gives the output for both fixed and moving targets. The Doppler shift causes this variations in the phase difference. Okay. So the detector output will goes to the delay line and amplifier 1 line. So the delayed output is amplified by the amplifier 2. Okay, once here the delayed output is amplified by using this amplifier 2, and undelayed output is amplified by using the amplifier 1. So next, the amplifier 1 and amplifier 2 outputs are given to the subtracting circuit. So in this, the echoes of the constant phases due to the stationary targets will be cancelled out, but the echoes of the changing phase due to moving targets are not cancelled. So the output of the display is the subtractor circuit output will goes to the display unit. In that it will produce a moving target echoes. Okay. This is all about moving target radar. Next one is the principle of instrument landing system. Okay. So here the principle of our instrument landing system is used for the safe landing of the aircraft under four visible conditions like rain, fog, snow, or night times with a greater accuracy. So at that time we use this instrument landing system principle, which is used for the safe landing of the aircraft under four visible conditions like rain, fog, snow, and night times with a greater accuracy and reliability. So here the pilot must have the knowledge about this safe landing system of aircraft at correct position on the runway, because he has to know whether pilot has to know. Without if the pilot does not know this instrument landing system, the system total aircraft may damage or so the ILS, here ILS means instrument landing system, consists of a localizer, glide path equipment, that is a glide spoke, and market beacons. Okay, marker beacons. Okay, so this is the instrument landing system. So in that it has three parts: localizer, glide path equipment, and marker beacons. So first one is a localizer. Okay, so this is the localizer, so which provides a horizontal guidance to the pilot about the position of the aircraft, whether it is flying to the right or left or center of the runway. So this information will be displayed on the display of the pilot. Okay. So the function of the localizer is which is used to provide the horizontal guidelines to the pilot, that will be displayed on the display in the pilot. Okay. It is located at 300 meters from the end of the runway. Okay. So this will be located at 300 meters from the end of the runway. After end of the runway, it will be located at the 300 meters. Okay. And operated at 108 to 112 hertz. Okay. It has an antenna arrays providing a carrier modulated by 90 to 150 hertz of signals. It will provide. So whenever the aircraft will move to the right side on the runway, 150 Hz signal is stronger. Okay, so here it will produce two carrier frequencies, that is 150 and 90. So whenever it aircraft will move to right side, it will produce the 150 Hz signal. Okay, when the aircraft moves to left side on the runway, 90 Hz signal is stronger, and whenever the aircraft moves along the center line on the runway, two signals will cancel each other and zero position indicates on the display. Okay. So next, glide path equipment. So it provides the vertical guidelines. Okay. So first one is localizer will produce the horizontal guidance to the pilot, and glide path will produce the vertical guidance to the aircraft with a landing. So it is located at one side of the runway and is operated at 330 megahertz, and it is also has two antennas will provides the carrier modulated by 90 to 150 Hz signals. So when the aircraft is flying above the glide path, 90 Hz signal is stronger. Okay. When the aircraft is flying below the glide path, 150 Hz signal is stronger. See here, glide path. Okay. So whenever the aircraft will flying above the glide path, 90 Hz signal అనేది stronger ఉంటుంది. Okay. Next, whenever the aircraft is flying below the glide path, 150 Hz signal is stronger. Okay. And whenever the aircraft is flying along the glide path, two signals will cancel each other and zero position will indicate on the displays. Okay. So ఇందులో మనకి localizer will produce the horizontal guidance to the pilot, and glide path equipment will produce the vertical guidance to the pilot. Next one is a marker beacons. So these are used to altitude, that means height checking, and provide the distance between the aircrafts and runaway touchdown points. The information presented by this audio and visual methods, these will produce the fan shaped beams at right angles to the localizer. See here. Okay. Marker beams. So here thus the instrument landing system is very useful to the pilot for safe landing of the aircraft. Okay. Okay. Once again, you check and draw the continuous wave radar block diagram, all of you. Next, draw this diagram, that is MTI radar. This is the diagram of instrument landing system. Thank you.